Hi, this is Math2231 remote delivery for April 23rd, 2020. And the topic is use substitution in definite integrals. I'm reminding you of the key takeaway from part 1, and that is that students must be mindful of the limits when computing definite integrals using use substitution. I don't care how you do it, I do care if you get the right answer. So avoid mistakes, proceed with caution. This is where I left you off. You should have finished these problems. Let's see how you did. So here is the first integral that we were trying to compute. And you think about that for a while and you realize a good substitution would be this one. So u is 2w plus w squared. That means that du is 2 plus 2w times dw. It probably makes sense to factor that 2 out. So then we solve for dw, and we get dw is du over 2 times the whole of 1 plus w. And then we're being mindful of our limits. So as w goes from minus 1 to 5, we have to figure out, using this equation, what happens with u. u goes from minus 1 to 35. This is an accident that it ends up being the same number. That rarely will happen. And look what happens. Our substitution works. Magic happens. This 1 plus w cancels with that 1 plus w. And so magic did happen, and the use substitution can proceed. I'm jerking this 2 out in front of the integral. So I have that. I take the I add 1 to the exponent, divide by the new exponent, and do a calculation here with those numbers, and I get this. 35 raised to the 6th power must be a big number, and this is an enormous number. Sort of makes you appreciate infinity, though. And again, you do that, and then you substitute minus 1, which ends up being, actually, you're just subtracting 1 over 12. Actually, this might not be the exact number because you get an enormous number, and then you subtract 1 over 12. So I should have put an x through that. That's not actually the exact number. It's very close to the exact number. Actually, let's see. No, I think that is definitely not the exact number. Let's go to the next problem. Here's the one that we were confronted with to solve. And the same substitution will work for both. So u is equal to 1 plus 2x. That means that du is equal to 2 dx. That means dx is equal to 1/2 du. As x goes from minus 2 to minus 6. By the way, that integral looks like it's running backwards, right? Because it's going to, but it doesn't matter. You compute it anyway. So as x goes from minus 2 to minus 6, u goes from minus 3 to minus 11. What happens is that the substitution works. We just, magic happens. We just pull the 1/2 through the integral, and we have this. Here we add 1 to the exponent, divide by the new exponent to get this. And here we get a natural logarithm. And again, it's important that the natural logarithm have absolute values here because those things wouldn't exist otherwise. You do some calculation and properties of logarithms and so on and so forth, and you get this as your exact answer this time. Some would call that an ugly number, and I'm not going to actually finish that statement in the interest of time. On some of these, you might want to slow the pace down by pausing to take some notes and verify calculations. Here we have 2 terms in our integral, and it is wisest because we're going to be doing a different substitution for each one to break it into 2 integrals. So this is using properties of definite integrals. So on the first one, you know how to do this. The antiderivative e to the y dy is e to the y. So that's going to be an easy one to compute. Here you have to make a substitution. Here's a substitution that makes sense. So u is pi y, du is pi dy, and that means dy is 1 over pi. And we're going to be factoring out that 1 over pi through the integral when we make this substitution. And we're mindful of our limits. So as y goes from 0 to 1/2, u goes from 0 to, in this case, pi over 2. So then we do the calculation again. Magic happens, and we get this. We're substituting u values in. We do the calculation with the fundamental theorem of calculus for this one, and then the fundamental theorem of calculus for this one. Again, it's good that we know trig, right? And the sign of 0 is 0, so this is the answer to the problem. This is the exact answer to the problem. In normal times, I would expect you to certainly come up with this complete answer. Again, we know trig, so it is good. And again, we're going to have to break this into two integrals, do it term by term. Here, a substitution is going to be for this, and here the substitution is going to be for this. Okay, so we broke it into two, and we'll do each one separately. On the first one being this one, we're going to say u is equal to z over 2, du is 1/2 dz, and dz is equal to 2 du. And as z goes from pi over 3 to 0, u will go from pi over 6 to 0. It's a good thing we know trig, yes. In the second integral, this one, we're going to let v, I really want to use a different variable right now just so we don't confuse ourselves with too many u's. It's going to be pi minus z is v. dv is going to be minus dz. See, there's the minus sign there, and then that means that dz is equal to minus dv. Do not lose the minus sign or you will get a wrong answer. And being mindful of the limits on this one, as z goes from pi over 3 to 0, v goes from 2 pi over 3 to pi. Okay, so we're going to make the substitution, and you see that sufficient magic happens. We pull constants through the integrals. Again, I'm evaluating each of these in terms of u and v. I plug the numbers in and do the calculation, and I get this as my final exact answer. I like what I did last time. Let's try it again. Here are the final 7 examples that we're going to talk about. You know what to do and when to do it, and why don't you work on these before you look at the next part. That concludes part 2. I'll see you in part 3.